make an announcement before we start the next one. We have a free afternoon tomorrow. We don't have anything organized, but there's a number of things apart from staying here and doing math. For the fun things, you can go to New York City, I guess, unless you're having from Columbia. And if you just want to stay here in Stony Brook, there are two nice beaches in the walking distance. There's a really nice park, and also if you have a car, you can drive around. There are some other things you can do along the island. We have a lot of information. So tomorrow afternoon. So if you have any questions, ask me or ask the other ones. For now, we still have to go study the pre-afternoon right now.
The next speaker is Thurston, and he's speaking on a faithful action of the mapping class group from Heegaard Floer homology.
Thank you. So it's a pleasure to be here, and thank you, Robert, for the great introduction. And as usual, what I will say will also be joint work with Peter, who is skipping out, which is perfectly fine. Okay. So one thing, and I'll say a little bit, one thing that Robert explained is how from this theory of ordered Heegaard Floer homology, we get a action of the mapping class group of the surface on an explicit category, on a category of modules over some algebra. And so, and just to be a little bit more precise, this will come up. This is the action of the strongly based mapping class group, meaning that you fix a disk on the surface and you look at only maps from the surface itself that fix that disk. And the category is the category of, is the derived category of modules over an algebra. Well, the surface, or really a parameterized surface, Z. Surface F, parameterized by this point match circle. And and the theorem, as announced in the title, is that this action is faithful. And let me just be a little bit more precise about what part of the action is faithful. So there's a weight rating of this action. So for those who know a little bit about Heegaard Floer homology or monopole Floer homology, it's graded by the spin C structure on your three-manifold. And you have a spin C structure on the three-manifold. We're looking at surfaces across the interval. And if you can look at the spin C structure on the three-manifold and evaluate it on the surface, or evaluate its first term class on the surface. So you look at the spin C structure that we're living in, this first term class, that's a second cohomology class, evaluated on the surface itself. And this turns out to it can take values up from minus g plus 1 up to g. And so parts of this are known to be boring. If we look at the action on these extremal parts, the action is trivial, and that's been understood for a while. For instance, the fact that this action is trivial is how you'd find something like sutured Floer homology in monopole theory. So this is related to sutured Floer homology. And it's also related to plenty of other things. It's related to the fact that Heegaard Floer homology detects fiber knots, for instance, the fact that the action is trivial, so nothing interesting happens here. And so these sort of second extremal ones, these are the sort of next easiest case to think about. And here is the here are the cases where we're able to show that the action is faithful. Yes?
With the triviality for the extremal density structure, is that an isomorphism, or is it the identity? I mean, if you cut along a surface and then reglue by a different morphism.
So right, so specifically, right, I take any three manifold, I take any surface in it. I should take a non-separating surface so that it has so that we can talk about this issue. And I cut here and I reglue. If I'm in this extremal spin-C structure, the evaluation is this maximal now, then it just doesn't matter how I glued off there.
You get an isomorphic group, but it's not. I mean,
Is it the same versus isomorphic? I think this is something. I believe you get a canonical isomorphism, but I have to think about. I don't.
Is the external spin-C structure minus G or is it minus G plus 1?
It's minus G for the experts. It's because we're actually talking about a surface with the boundary component. Right. So in that action is faithful, and in the middle, the action gets harder to compute and presumably more interesting and presumably more remains faithful, but we're not able to prove that. And so I'd also like to compare this fact. You were getting a faithful action of the mapping class group on the category of modules over some surface. I'd like to compare that to a long-standing conjecture in the mapping class group literature, which is that the mapping class group of a surface has a faithful linear representation. And this is sort of surprisingly hard. It's still open. It's sort of there's good reasons to believe it's true. It's true for braids. It's true in genus 2. But not a lot else seems to be known. One reason why this would be an interesting conjecture is that having a faithful linear action implies lots of nice properties of your group. So this implies that your group, for instance, is residually finite. That for any element there's a quotient, there's a finite quotient where you see the element, or that it satisfies the Tits alternative. And a number of other consequences. However, these are all true for the mapping class group. All true and known to be true for the mapping class group. So it would give sort of another way to prove a lot of other things that we know, but it's sort of part of the question by itself. And so we don't prove this. We get an action not on a linear vector space, but on some category of modules. And in particular, we don't prove this, and in particular, if you take our action, you can extract a linear action from it by decategorifying, by looking basically at the action on the Rothendy group of this algebra. And that action is definitely not faithful. If it were ray groups, I would say it would coincide with the Borel representation, except that we haven't actually checked that. And this is mapping class groups, not ray groups. But I believe it is a well-known and not faithful representation.
Does linear here mean finite dimensional?
Linear or finite dimensional, right. And I guess that is an additional thing here. I mean, the Rothendy group, if you decategorify, you do get a finite dimensional representation, just not a faithful one. prove this conjecture. However, this is interesting in its own right. And one of the reasons why I find it interesting is it's more than just saying that it's faithful. We also get a geometric characterization of some of the algebraic actions. And in particular, you can detect intersection numbers on the surface in terms of the ranks of certain of some of the bimodules related. And also, it's not just an action on sort of abstract categorical modules. You can detect this with sutured manifolds, which I don't think I'm going to define, but just I can say more about that for anyone interested. So, in the last comment before saying much more is that this whole approach was inspired by the approach by the Chovanov-Seibel's work. They proved, in the context of a rate group action, they constructed an action of a rate group on an appropriate category and proved that that was faithful. And it's in fact, like our proof is in fact quite similar to theirs. For instance, they also got this characterization with intersection numbers and for essentially the same reason that we'll see. Great. So that's the statement and some background. And so now I'd like to go on to start saying things about the proof. If there aren't any questions here. So Robert already said a lot of what I'll need about ordered Heegaard Floer homology. Let me just remind you a little bit. So to a surface, and really I want a parameterized surface. Parameters, the surface associated to some pointed match circle. You associate an algebra, A of Z, a differential algebra. To a three-manifold whose boundary is a particular surface, you associate a module, CF hat of Y. And I want to be a little bit vague about, well, Robert was thinking about CFD for some of what I'm going to say. It's a little more convenient to think about CFA. But the distinction really doesn't matter very much, so I'm just going to write CF hat for this talk. And if you have the three-manifold whose boundary is not connected, but is a union of two surfaces, for convenience, we reverse the orientation of one of them. We get, again, a chain complex. Here, this is now going to be a differential module with the left action of the one algebra element and the right action of the other algebra. The left action of A of Z1 and a right action of A of Z2. And gluing three manifolds along their boundary, this corresponds, well, Robert described it in terms of a Hom complex. You can also, but that involves some orientation reversal, which is sometimes easier to avoid. Let me just say it corresponds to some appropriate tensor product. And And so a particular case that gives us the mapping class group action is when you look at a mapping cylinder. So you look at, so if you have some map from two surfaces, between two surfaces of the same genus, possibly parameterized in different ways, you look at the product map, f of z1 across the interval from 0 to 1, and you parameterize the two boundary components in two different ways. The left boundary you parameterize by the identity here, and you parameterize by the identity on the left, identity across 0, and on the right you parameterize by this map phi. And I got things backwards. This map should go from f of z2 to f of z1, the way I have things set up. In any case, to this we associate some bimodule CF hat of phi over these two algebras in a compositional way. And so one reason why I'm being a little vague with a lot of the details here is that a lot of it doesn't matter. So in particular, for this is a module, this is a differential module over the algebra, but actually I don't need to know anything about the action of the algebra. All I'll need is what the differential is, the internal differentials, none of the sort of things that make this theory particularly hard, or harder than the ordinary Heegaard Floer homology. And so we're getting out these bimodules over A of Z1 and A of Z2. And you have a chain of these, you start tensoring them together in the middle, that gives you a compositional map. So phi goes to CF hat of phi. It's compositional, meaning that phi composed, if I look at CF hat of phi composed with C, that's CF hat of phi tensored with CF hat of C. And this is a slight lie. Let me underline this in red. Again, this is slightly corrected, or you need to use slightly different models in order to get that to be true on the nose. But it's pretty close to true, and in any case, you get an action on the categoric modules by tensoring them. So, and that's the action of the mapping class group on this category. So one thing I realized I forgot to ask anybody, I don't have a working watch. Does anybody have a watch I can borrow to keep track of the time? Thank you. Yes, that's great. Thanks. Thank you very much. Yes?
So in this new extreme case, the alpha was not particularly simple. Can you write them down?
In the extreme case, in this case, the algebra is indeed. I will not actually, or I was not planning to. Excuse me. It is simple. It's sort of about as complicated as it was in the torus algebra case. In particular, there's no differential. I could write it down if you want. Ask me again later. I don't have the invitation for it now if you want to know. Right. So so I want to say, and so okay, so how are we parameterizing the surface? Let me, in particular, what I need to define the algebra is this notion of parameterizing the surface. These are the pointed matched circles. Pointed matched circles, as Robert was describing them. So you take some circle, and then you somehow pair up the points. Fine. I'll tell you what the algebra is. Sorry. So this is the data, and I'll say more about that data in just a minute. But since you're asking, I'll tell you what the algebra is. So the idempotents correspond to pairs of matched points, and the sort of elementary generators correspond to these intervals between adjacent pairs of endpoints. Or sorry, let me say the non-trivial elements correspond to intervals connecting endpoints. So you get, it's again a quotient of a quiver algebra here. So we'd have one generator. So if we label these pairs 1, 2, 3, and 4, you'd have, and I'm doing this on the spot, so I hope I get it right, 2, 3, and 4. We have these idempotents, and then we'd have generators going from 1 to 2, from 2 back to 1. Here's 2 back to 1. Then we have a 2 to 3, and the 3 back, sorry, that's not 2 to 3, that's 1 to 3. And a 3 to 2, and a 2 to 4, and 4 back to 3, and so forth. So these are the generators. These algebra elements that don't correspond to the short chords. Longer things are products of these short ones. And if I try to multiply two chords whose endpoints don't match up, I get 0. That's the algebra. Okay, but I did want to say more about the topology. Another way of thinking about this pointed matched circle is that this is really the same thing as a perfect Morse function on the surface. I start off with a single index 0 critical point, and then I add some index 1 critical points. Some handles, and then I add a single index 2 critical point at the end. And we need we also have this pointed matched circle, which means we picked a particular base point here, which means we also, that in terms of Morse dyadic functions, we're going to add an extra disk at the end, and that's going to correspond to picking a flow from the index 0 to the index 2 critical point, plus choice of, rather the other way around, flow from index 2 to index 0. And one thing that we can do to a Morse function is we can negate it. You can turn it over and think about the negated Morse function. And I'll call it and that itself is another Morse function, and it corresponds to a different pointed matched circle. which I'll call the dual point in that circle. And write Z star. And I'm going to write down the answer in this case, but you'll have to think for yourself about how this corresponds. So you draw here, and we have an index 1 critical point in the center of each handle, and I'm drawing the flows from the index 1 down to the index 0. And we also have the flows from the index 2 down to index 1, which I'll draw in blue. And now I want to turn this over and think about the blue arcs as sort of the base arcs, and walk around this boundary here and recording which blue arcs I see. And if you do this exercise, okay. Let me erase something I just wrote because I don't want to go to the other end of the board just now. Okay. If I turn it over and think about what happens there, I end up with a different pairing, specifically this one. So again, each of these corresponds to a handle. And now, what wasn't read before, well, so now the blue ones are running around like this. And the reds are just running across.
What do you have?
Say again?
You have a fact. The number of handles increased.
Yes, it did. Why did that happen? Did I do my computations wrong? I did my computations wrong. I'm sorry. Thank you. The correct pairing, that's what I get from trying to do things from memory, is this one. And maybe one nice way to think about it, I mean, it's hard to draw the index 0, the index 1, and the index 2 pictures, handles all in the same picture. So the easier thing to think about is to just forget about the index 0 and the index 2 handles and just look at kind of a neighborhood of the index 1 handles, maybe with a little extra strip. So, and also cut it at this flow line. So if I just look at this diagram here, this is the same as this surface is the same as with its markings by blue and red is the same as this surface, except I switched whether I draw blue on top or blue on the bottom. So these two are homomorphic. So right, so there are two different markings on the same underlying surface. So really, the nicest surface to think about is we have my surface F, and I want to think about a kind of open subset of F, which is F minus a bunch of things, minus the a neighborhood of the 0 handle of the disk at the bottom of my Morse function, neighborhood of the 2 handle. And I also want to remove a neighborhood of the flow z from the 2 to 0, between the index 2 and the index 0. Did I remember to give that name? I erased by now. Then we call the special flow line z. So these 2 together actually form a single disk. These 3 together all form a single disk, and it's kind of a canonical disk that only depended on my Morse function. So this is an open surface, and so z, and it's also the same surface that I brought up there, z and z star are 2 markings on this open surface with endpoints in different parts of the boundary. And this sort of stronger theorem than just that the action is faithful is what will give me some geometric information about from the Heegaard Floer homology. That if I look at any map phi from between 2 surfaces, f of z2 to f of z1, and I want it to be a strongly based map, which again means it fixes a disk, and I want it to fix that disk. So I want to think about it as a map between these open surfaces. Then I can look at, we associate an invariant an invariant associated to that surface. Differential module, it's only an invariant up to homotopy, so if I want to get something invariant, I need to take the homology of that chain complex. And I just take its rank, the total dimension there. And that, I claim, is equal to the geometric intersection number between z1 between z1 and phi of z2 of the dual complex, the dual chain marking to z2. So this means this is the geometric intersection number. I think about these, there are 2 different collections of arcs on the surface, and I just count the number of times, the total number of times that they intersect each other.
No signs.
No signs. That's what geometric rather than algebraic means. And so, for instance, if phi were the identity, I conveniently have a picture of that right up over here. And each arc on one side intersects exactly one arc on the other side exactly once. And so I get, 4 in that case, or in general, twice the genus. And that's going to be enough to imply that the mathematical action is faithful using the this lemma. So again, given a map between these 2 surfaces, phi is the identity if and only if this intersection number is equal to twice the genus of f. And it's all, otherwise it will be more than the genus. Yes, Matt?
Is that the minimal geometric intersection number?
Yes. Okay, let me say something about this proof here. So we start off with our F open of one of the surfaces. And so Z1 is sitting here in some nice way, intersecting the kind of lower half of the boundary. Now these arcs Z2, they can't be trivial. They can't be boundary parallel on the surface. But on the other hand, the arc Z1, if I cut along all of those arcs, I'm left with a planar surface where everything's boundary parallel. So every arc Z2 star in the image of Z2 star has to intersect at least one of these, or else it's trivial. And if it does intersect something else just once, then it's exactly one of the arcs that we just drew. And also, but if we had something which was maybe I did a Dane twist, like I can imagine maybe phi was a Dane twist along this curve here, and that's going to change what Z2 is. It's going that I have it go around the Dane twist here. And I picked up these two extra intersection points in this case. So I get a bigger number here than I had before. So here, if I count the number of intersections, I have 6 intersections rather than the 4 I had before. Yes?
So could you remind us, so CF hat of phi is this bimodule?
Yeah.
So what does it mean to take its homology?
So it's a differential module over the algebra. And I just want to completely forget about the algebra action on the two different sides and just look at the kind of internal differential. And this is, the fact that I'm doing this is why I don't need to know what the algebra is.
And, I mean, is there any intrinsic description? I mean, like, how does this compare to, like, what you get when you glue the two ends of the form of the mapping cylinder or something, geometric?
Right, so I compare, there's a spectral sequence from this to the Heegaard Floer invariant of the mapping cylinder. I think that you can't look at just the invariance of the mapping cylinder, or if I want to prove that I detect mapping class rebalance, because the mapping cylinder might look like a surface cross an integral, even for some non-identity element here.
Is the content of that theorem that, I mean, the boundary operator is trivial?
What?
Is the proof of that theorem that prove that the boundary operator is trivial?
Exactly.
You said there's a special sequence from the mapping cylinder to that?
So what Jake was asking about, I can look at, what's the stand? How do you write the mapping cylinder? The mapping cylinder of P, mapping torus, rather, where I take this mapping cylinder and I identify the left side with the right side. And one theorem, which is that the CF hat of the mapping cylinder, or the mapping torus, let's call it T sub phi rather, T sub phi, mapping torus, is computed by computing Hochschild homology of CF hat of the mapping cylinder. Which is a bimodule over A of Z and A of Z. So, so if you don't know what Hochschild homology is, that's okay, but essentially I'm using these two actions to kind of add some extra differentials. There's always a spectral sequence from the homology of a bimodule to its Hochschild homology. Wait, is that right? In this case, there is anyway. There's a spectral sequence from here to that side. Anyway, there's a spectral sequence from here to here. This one's smaller. The homology here, we have that geometric interpretation. The homology here has some other geometric interpretation, but it's not just given by intersection numbers. It can be smaller.
So that the spectral sequence collapse in general case, like a large part of the signal.
If you say so. I can believe that, yes. I don't think it's always...
Well, I don't know, but I can believe it.
That what?
Well, I can sort of believe it.
That it collapses?
Well, I don't know, but...
Okay, I haven't... does the spectral sequence ever, from here to here, collapse in some cases? Say again?
From where to where?
From the homology of the bimodule itself to the homology to the Hochschild homology, like going from the mapping cylinder to the mapping torus. Okay, we don't know. In any case, it's not what the theorem's about. Yeah, right. Right. But again, this one here is just ignoring the module structure. And again, for experts in the audience, if you, to be precise, I'm really talking about exactly not what Robert was talking about, but CFAA. You can say things in terms of CFDD as well, but it's a little bit different. Okay, great. So, now I would like to say a little bit more in order to prove this theorem. I'd like to say a little bit more about how you actually compute CF hat in general. And partly this is just about how you compute Heegaard Floer homology. So you start off, I guess I'm not going to repeat this, you start off with the things Robert was drawing, these bordered Heegaard diagrams, which have, let me just summarize, you have some surface sigma, which is not necessarily the same as the boundary, but just some other Heegaard surface, sigma. And you have two collections of curves. Collections of alpha curves and beta curves on the surface, which are good enough to form a Heegaard collection. So I should have said this is with boundary. In the case where it's bordered, so that the complement of the union of the union of the alphas and the complement of the union of the betas, these are both planar surfaces. In the usual Heegaard diagrams, you take a collection of circles and you cut open until you can't cut anymore and have something still be connected. In our case, where you don't necessarily have enough circles, but then you add some arcs to my collection you add some arcs to that collection of curves, so that it still ends up being planars. And then, and with another condition, so each component of the boundary of the surface needs only alpha arcs or beta arcs running out to the boundary, and furthermore, it's going to be appropriately based. Like everything in the story. So For instance, I don't have to draw you the picture. This surface is an example, or it's nearly an example. If the boundary is connected in this case to make it really fit that definition, let me join up the two endpoints, and then the base point is sitting kind of there. So this has two boundary components. One side is meeting only alpha arcs in red. And the other side is meeting only beta arcs. So this is, right, these are alpha-beta bordered Heegaard diagrams.
Why the complements in both cases
You're asking, like in this example, or why do I require that?
Does it mean that each of these...
So first of all, so in this case it's true. Like if I cut along all the blue arcs, for instance, it just sort of manifestly becomes a planar surface. In this example, yeah. So I want to... I'm sorry, I thought this was enough.
Heegaard diagram is for manifold with boundary, right?
Heegaard diagram is for a manifold with boundary. I want something that represents a manifold with parameterized boundary. So if I forget about the parameters, I can forget about the alpha arcs and beta arcs at all, but I want to add enough alpha arcs and beta arcs so that it's completely parameterized. And this requirement, sorry, I thought this would be enough. I think I also want
I thought about them as meridian.
maximal with this condition, right? Well, as in the example Robert had up, I mean, you want both the meridian and the homology. You want a complete marking of the boundary. For instance, if it were a torus boundary. Great. Right. So for instance, that diagram, that's a kind of special diagram, which we'll be using in our proof. So this dualizing Heegaard diagram, which I'll give a special name, I'll call it G and Z star, marked by Z on one side and Z star on the other. So, and this represents a three-manifold. Since Robert already said this, I'll just remind you, you start attaching handles along the disks along all the circles that you see, all the alpha circles and all the beta circles. Actually, I'm writing. So we attach disks along the alpha circles and the beta circles. And one interesting special case is when we have no alpha circles or beta circles, like in that dualizing diagram, in which case we don't do anything to the surface. You just thicken it up, and that's your three-manifold. So in this, and in that case, I mean, that's the kind of connection. That's the connection to, like, for the diagram for some mapping class group element, we want a surface across an interval just marked in different ways. And so we can do that kind of thing here, just take this surface across an interval and just have different markings on the two different sides. So I just need just a small amount more from Heegaard Floer theory. So I also need to know what the generators are. So the generators are collections of points contained inside the union, the intersection of the alphas and betas. Some subset of these intersection points here, and with some restrictions, with exactly one element on each alpha circle or beta circle, most one element on each alpha arc or beta arc. So, again, in this case, the generators would just correspond to subsets of this collection. There are 2 to the 4 different possibilities in this case. And one particularly interesting thing to look at is the weight. If you remember back from the beginning of the talk, there is weight ranging from minus to G. The weight of the boundary component is equal to the basically given by the number of the size of the subset, the number of occupied arcs touching that boundary minus the genus. And to be honest, it really is plus or minus this, depending on whether it's alpha or beta circled. So, in particular, in the second-extremal case, what we're looking at are just we'll have exactly one such thing occupied. So 4 generators in this case, rather than 2 to the 4th. And the last thing that we need are the differentials. So, and so the differentials where we count, there's some count of some sort of appropriate type of pseudo-homomorphic curves in some appropriate symmetric power of sigma. So, pseudo-homomorphic disks, I should say. We count disks mapping into the symmetric power of sigma with one endpoint mapping if we're supposed to have a differential from x to y, we want one endpoint to go to x and another endpoint to go to y. In the boundaries, one goes to the alpha curves and the other goes to the beta curves. So some appropriate map like this, and this is a little bit hard to visualize because we're dealing with potentially some very large symmetric product of the surface. But if you think about, for instance, this case, for this dualizing surface, and in the second-extremal spin C structure, the weight where we only have one point occupied, in that case, we just have n equals 1. We're looking at the first symmetric power of the surface. We're counting homomorphic disks embedded inside of the surface, which is something that is actually very easy to do. We're counting bigons in the surface, counting curves looking like this in the surface, which just boils down to counting a bigon sitting inside here. And the constraint that it be pseudo-homomorphic is not a constraint by the Riemann mapping theorem. That you can if I find some bigon like this, I can always find a map from here to here.
I'm sorry, I get confused why we're studying why the symmetric product varies with the weight here. I mean, are you using some identification with a different picture?
So this is not. I mean, I mean, my generators correspond to subsets, as I said, like, and so in this case, subsets of these intersection points. And, you know, if I only have two intersection points, like that just doesn't live in the third symmetric power of the surface, it lives in the second symmetric power of the surface. So of course I should be looking to maps to the second symmetric power of the surface rather than the third. Yeah, I mean, in the other settings, like if I'm looking at closed diagrams with no arcs, then I'll always have the same number of circles and it'll always be to the same symmetric power. But here it's just, it does vary. Because I'm looking at this alpha-beta bordered context. Yes?
I think maybe another answer to that question is that if you form a natural way to form a closed-up object, you get some sort of piece of that which is sort of very standard, and then there'll be a bunch of fixed points, fixed intersection points in there. And so the question of how many intersection points there are on here, or how many fixed.
Well, I guess I was wondering if, you know, I mean, you have these fixed points, these fixed intersection points, and so, so you would be considering a much larger symmetric product, but you reduce it to a case of a lower one somehow. By an argument, but it's not naturally.
Let me try to say that in other terms. So for a particular Mapping-class group element, like if I wanted to construct a diagram for a Mapping-class group element in the sort of original sense, so you can consider the diagram I'll call G of Z1, B of Z2 star. So if I've given some map of the type I've been considering, instead of taking that boring diagram I had over here, I can take some complicated Mapping-class group element and look at the image of those arcs, like I have here. And this is another example of a border diagram, at least if I do this thing. But this is not not the one that you would actually use to compute CF hat of the module. So CF hat of phi is not the complex of this one, but it's the complex. You take basically you take this diagram, and then I glue on the dualized. I kind of turn things upside down twice. I go from Z1 to the dual to Z2, and then from the dual to Z2 back to Z2. And this is the original diagram. And so what I'm looking at here, I'm looking at a case where there's one intersection point on this side, and then necessarily you're kind of forced to have the genus -1 intersection points here. And there your counts are more complicated, but on this side your counts are quite simple. Right. When did I start? Okay, so let me say the punchline here. That if I look at the invariant of this piece, if I look at this diagram here, like I have over here, if I arrange it to intersect minimally, one definition of geometric minimal intersection is that I have no bigons, and therefore no differentials. So if I totally forget about the action of the homology, the rank is just given by exactly this this intersection number here. And then you have to work just a little bit more in order to see that. Sorry, and then adding on this extra piece doesn't actually change the rank at all, because basically, well, It doesn't add any extra differentials. Any possible domain on this side that touches one boundary component also touches the other. So it doesn't add any possible domains that don't reach the boundary at all. Okay, so let me stop there and ask for questions.
I'm still confused about the passing to these alpha beta Heegaard diagrams. And I mean, if you were to draw, I was just getting used to this, the
Alpha Gordon diagrams, right?
My modules that you used to draw with just alpha corresponding to the boundaries. And for those, you can just, if you want to construct the mapping torus from quantities, and you just bring the two ends together.
Right. And for this, you can't glue the two ends together because they look different, so you have to glue on this extra piece.
Or you have to take off this extra piece.
Well,
put on this extra piece in order to get the...
I mean, it's a dualizing thing. If I glue this to itself, and again, that's the same as just having one or doing it to its... Yes, Matt.
Various geometrically interesting monoids in the mapping class group or grade groups. I was wondering, somehow most of which involve some notion of positivity. And do you have, does this give you obstructions to say, a mapping class being realized as a product of positive Dane twists or a quasi-positive grades, this type of stuff?
That's a question we have not thought about at all. Do either of my co-authors want to?
Can you repeat the question?
The question was, do we get obstructions to a mapping class group element being in one of the geometrically interesting monoids, like product of positive Dane twists? I agree, it's a great question, and we haven't thought about it at all.
And do you get bound for commutator?
Do I look at say again?
Do you get a bound for stable commutator?
Do I get a bound for the stable commutator length or the commutator length? Again, we haven't thought about that at all. Yes, Tom?
Can you prove any of these properties that mapping class group is known to satisfy?
Like for instance, can I prove the Tits alternative or that it's residually finite?
Yeah.
That we did try to do a little bit, and we have not done.
And is it hopeful that that's enough structure to do it, or is it?
For instance, maybe you want to see that this is residually finite. So maybe you want to find some, like it would be enough to find some quotient of this category of modules, which actually is just finite. And of course, the mapping class group can't act faithfully on any finite set, but maybe you can find some sequence of quotients on which any particular element eventually acts non-trivially. That's conceivable, but it's also an interesting question, but again, we don't know how to do it. The Tits alternative seems harder.